So in last class we were here. So as far as your exit points are same, so you will get same energy here. So no, because here fluid is entirely connected here. This is also connected. This is also connected. So you are getting same thing. So whatever potential energy is there, same energy actually would be converted into your kinetic energy here. Fine. Now this is what you have, that entire thing would not be converted. So what you have there, that energy would be put on some particular blade something, and blade will have its mechanical efficiency actually. Okay. So in that case, uh, so in that case, your energy available for a mechanical work or a, let's say, pump would also decrease based on the efficiency. So what pump is doing? Pump is converting your actually your electrical energy. Uh, First is motor actually. So motor is converting your electrical energy into mechanical energy. It rotates the shaft. Now that shaft is connected to the pump. Now that pump actually that pump converts your mechanical energy into a kinetic energy, which transfers to your fluid actually. So what does the turbine do? So turbine is actually converting your potential energy of a fluid which is heating on a particular blade of the turbine. So that turbine is getting converted into the electrical energy. So you have some purpose. You have a shaft work, you have a pump work, and turbine work. Fine. And each of the equipment have some efficiency actually. So based on that, everywhere you will find efficiency. The mechanical efficiency here, then you have efficiency of the pump, then efficiency of the turbine. Fine.
Yes, sir.
So the next slide. So this is what you have the here actually. So means the efficiency of the motor is being calculated by mechanical power you are providing, and electrical power you are providing, mechanical power you are getting out from the mean the motor in terms of shaft work. That is the efficiency of the motor. Efficiency of the generators. So generator practically is your actually is your turbine there. So you are means somehow you are the rotating its shaft, and that is producing your electrical power. Now you are combining, because pump will not run its own. So you will combining a pump, you are clubbing a pump with some motor. So your combined efficiency would be multiplication of the two, efficiency of the pump and efficiency of the motor actually. So finally you are means putting a electrical work to the motor, which is converting into the mechanical work in terms of shaft. Fine. So this is how you are means converting it. Now, may I mean the request all other people don't to use their annotations and writing mouse and all that, because it's just creating something. Uh, Now this is the part here, efficiency 0%, 100% and all this. So 100% efficiency is never possible, because there is always some conversion, because you cannot convert one form of the energy into the another form without any loss actually. So that is you can say would be against the rule of thermodynamics. Entire thing cannot be converted. Fine. So there is always some loss actually. Now this is actually one of the example here how the turbine actually gives you energy. So in the turbine case, you actually having the water at a particular height. So in that case, it have a potential energy here. Now that in the below of that you have a turbine. Turbine is practically a blade actually, on which you are putting the water from a particular height, so that potential energy at this particular end of here is being converted into the kinetic energy actually, so that mgh term here, the whatever for potential energy available here, that is the mgh, the total, the height of the water multiplied by mass and g, so that is the mgh. So that particular energy now is being converted into the kinetic energy the time it hits the turbine blade. So blade move with some particular velocity, then RPM. And then that mean the rotate the shaft of the generator, and then generator produces the electrical energy to you. So that's what your mechanical shaft is being working actually. Okay. So this is one of the work means the example here. So whatever here at this particular point, you are putting some pressure here. So there's atmosphere, open to atmosphere here. So you are here. So then everything is being converted inlet and outlet velocity at this particular point, because you are all means you are throwing the water from point 1 to point 2. Both are open to atmosphere. One is going to the river, and then both the places you are having velocity equal to 0 here, because both are free surfaces of large the reservoir. So what are you the converting? This much total potential energy you are converting into the actually the electrical the energy here, considering 100% efficiency of that. So that's what your mgh term is being converted to your electrical means energy. If your efficiency is 100%, by chance is not 100%, multiply by that value here. Okay.
Yes, sir.
Okay, sir.
Huh. So this is what is being just calculating efficiency part. Here you have the mass, here mass flow rate. This is what you got the previously from mgs term, gs term here, you multiplied here. Then you are the, here you are taking electrical work, this because you are taking the 95% efficiency of that. So you have the multiply this value by 95%, 0.95, and then you got this value. So this is your overall efficiency of that particular turbine. Now, before that, after that, we want to design our pipeline. So this is what we already talked about. I am the requesting again, don't write anything actually, please. I don't know how this is getting to have typed and writing, because I don't use anything such thing. But this is unnecessary, creating some problem.
So you can turn off the permissions in settings, I think.
Okay,
Yes, sir.
because
Annotation settings.
yeah, I'm doing that actually, because I just clicked it, because then we have conducted so many things, but here I don't know what is happening, because this, so annotation, I don't want to draw it actually. So what to do here? Clear out, clear all driving, fine. And then what to do? That much is fine, I think. Others should keep your mic mute actually. I don't want to draw, then what to do? Now it's fine, I think. So this is what we are talking, that in case of energy of the fluids, actually you, again, this is Chirag Shetty, what is happening? Please
By
just let me
mistake, I
conduct the
clicked
class actually.
Sir, by mistake, I clicked it. I'm sorry for that. Sir, I was opening the
That's,
app.
I can understand, that's fine, but how to handle it from my side? I'm just,
I have written that my name. Why will I do?
Oh, please don't do
By
anything. एक छोटा सा टाइम मिलता है and that also could be because something like that. Anyway, so what we have there is that when you have a pipe and all this, as we talked, that's due to non-ideality and all this. So this is what you have. This is energy at two ends of the pipe. One end is this at 0.1. This is another end is 0.2. And what you have in between of that auto accept. Even if I want to use this drawing, this will automatically will come. What is this nonsense? Anyway, so you have this. So the difference of the two is called a loss actually. So that's called here HLT. This is the loss due to non-ideality, due to some sort of frictions in the pipeline, something. Now this need to be calculated. How this loss will come, I will tell here. This part we have already talked that actually. So the losses in the state pipeline would be calculated F L upon D B square upon 2. Actually, you should use this one, B square upon 2G. This is calculating loss in terms of meters of fluids actually, okay? In terms of meters, and if you want to convert this in terms of energy, just multiply by a term here. This is a meter, so you can multiply by a term of GH only, right? Mg actually. So Mgh is called the energy of the fluids. Hello? Anyone wants to say something? I would request all participants to mute their mics actually. So this part we already talked that the Reynolds number actually just to calculate that, just to have a loss coefficient something. Now this part we already talked that flow pattern thing. Then this is what we have talked also in the last class there, that how to calculate a friction factor. So friction factor for the laminar flow, we have the 64 upon RE. This we have derived in the last class by taking from Poiseuille equations. Is this fine or not? This we have derived in the last class. This we got the 64 upon RE for the laminar flow in pipe.
Yes, sir.
Right. So next one is because the laminar flow is the one of the condition. Another condition is turbulent flow. For turbulent flow, there are the several correlations just to calculate the friction factor. So this is the one of the correlations which I found good actually. So this is one actually, 1 upon under root of F minus 2 log 10. This is log 10. Epsilon by D upon 3.7 plus 2.51. So this is actually have friction factor here, both the sides here. So this is always become a tedious formula just to calculate a friction factor. So we have another formula here. This is called a Holland correlations. So this is easy actually compared to a Colebrook means the formula there. So you have 1 upon under root of F minus 1.8 of log 10 epsilon by D upon 3.7 to the power 1.11 and plus 6.9 upon RE. So first you calculate the value of RE your RE value is less than 2300, use the 64 upon RE. I'm requesting other to make mute your mic. And next is, once you have actually a RE value more than 2300, use this formula. What you need here, epsilon. Epsilon is the roughness of the pipe. It's just a zigzag type of the surface. How rough is the surface is being calculated in terms of meters or centimeters with respect to the diameter of the pipe. So epsilon is the roughness. How rough is the surface? Means that if you will move the hand, it should move something like that. So how much is that depression type of thing? That is treated as the roughness only. This is another correlations in case of the the smooth pipe. So this is also there, 0.316 RE to the power 0.25. A smooth pipe means you got a rough pipe. Now you are making it the smooth. So what do you do to make the means a rough surface to make it smooth? What do you do? If you have a rough surface, you want to make it smooth. What do you do actually? Can anyone tell? Can anyone tell? So one thing is that either you polish it by some paint or something, or by some metallic polishing, or you grind it by a fine grinder. Hello? So that way, or you just take a sandpaper, emery paper or sandpaper, keep in rubbing it again and again, and you will get the smooth surface. But what will happen after a particular time, you cannot smooth it beyond a particular point. So it would have the roughness, there could be a bare. So Soumya Burma, please mute your mic. So in that case, what you have there is that you cannot smooth any particular the surface beyond a particular point. You can do all sort of thing, and those type of the surfaces are called hydraulically smooth pipe. Means you did your best and you cannot control the roughness beyond that particular point, and those surfaces is called a hydraulically smooth surface. And for those cases, the friction factor would be calculated by this, that F is 0.316 RE to the power 0.25, and this is actually for RE greater than 10 to the power 5. Okay. Now this part we already talked that what is this hydraulic the diameter and hydraulic the radius. So last class we have talked about that hydraulic the radius is your area for flow divided by the perimeter in which the fluid is in contact of the surface, only that much perimeter. So this is called cross-sectional area for flow upon wetted perimeter. This is called hydraulic the radius. Multiplied by 4 is called hydraulic the diameter. This is need to be calculated in case of non-circular surfaces. Okay, so this we have already talked about that in case of the rectangular duct something. And these are the actually your various shapes, and where you can calculate your A by B ratio, and this is corresponding values of the actually friction factor. So practically you need not to remember any one of them. This is just to show them that is for laminar flow. If you want to calculate the friction factor, in case of pipe, this is 64 upon RE. In case of rectangular duct, if A and B are same, you are getting this correlation. So this would change depending on that, because your hydraulic diameter is getting changed. So therefore these values are getting changed. Okay. Fine.
Yes, sir.
So only thing you have to remember only this expression 64 upon RE only for a smooth means only the circular cross section. Rest of the thing need to be calculated That time you will calculate from hydraulic the diameter only. After that, you should calculate it only. So you need not to remember. This is just a way to show that this is how the value changes. Now, once you know your friction factor, this is again actually a Colebrook means your thing, Colebrook correlations, smooth and the rough phi is valid for all the RE value. This is a Holland correlation. It just need a value to be substituted on the right hand side, and left side your friction factor can be calculated. And this is the roughness corresponding value of the friction factor, and these values would be provided to you. You need not to worry for that how this would be provided. Means if you want to use this particular formula, for you epsilon mean the roughness of the material and diameter would be provided, and RE would be calculated by you based on your volumetric flow rate and the diameter. Fine. So these are the barrier, the materials, and these are their corresponding value of the roughness, which is your epsilon value here. So for that case, what you have here, glass actually, glass or plastic is being considered as a smooth material. For that, the roughness is being considered as 0 only. Concrete, you have here, the roughness value seems to be extremely high here. The concrete, if you don't put a cement means coating at the later on, so the concrete is highly the rough here. So in terms of mm, the roughness is 0.9. In terms of feet, the roughness is 0.003. So either of that would be provided to you. Wood, you have 0.5. Rubber, again you have 0.01. Copper means the material, copper or brass tubing, you have 0.0015. Cast iron, you have 0.26. Galvanized iron, you have 0.15. Wrought iron, you have 0.046. Stainless steel, you have 0.002. Commercial steel, you have 0.045. These are the roughness values which would always provided to you. But from interview or from some point of view, at least you should know some base material. Let's say glass. If somebody asks the roughness of glass, you should give the answer. It is 0 actually. It's considered as a 0 only. Concrete is one of the material is being used all to make the sewage pipeline or a big water pipeline. So you can tell the 0.9 to 0.9 to 9 actually. Then at least copper. Copper is most copper or galvanized. You have here 0.15 for galvanized, and brass or copper is 0.0015. So there's some value you try to remember which are most commonly used materials actually. Okay.
Okay.
Now, based on previous correlations, these graphs can be prepared, which are the function of the Reynolds number, and this side is your friction factor. So y-axis is friction factor, Darcy friction factor, and then you have x-axis, you have value of RE in terms of log plot. And these the lines, each line correspond to particular roughness, epsilon by D, which is called the relative, the roughness of the pipe. It can be for any the material, and for example, these values are given to you. The roughness values are corresponding to the material. You have here glass, concrete, wood, rubber, copper, cast iron, galvanized iron, wrought iron, stainless steel iron, and commercial steel. These values are given. So these chart would be available to you in most of the books and all calculations, either chart or correlation. So from the reading of chart, generally in case of the simulations or calculations, creates the problem because you cannot read because the values are there in log, because from here one column to another column values are getting changed by 10 times, or let's say 100 times somewhere, because these are in the log plot. So slight change in the reading will create a huge variation in the data actually. So therefore you are always supposed to use this Holland correlations or a Colebrook correlations just to calculate your friction factors. Okay, fine.
Yes, sir.
So this is the another graph of the previous one. This is the another version of that from the different book. This is from Fox actually, McDonald Fox. So this is again the same graph. You have here the roughness value of RE here on x-axis. Epsilon by D are the lines here corresponding, each line corresponds to particular epsilon by D. Let's say the first line corresponds to 0.05. So epsilon by D value is 0.05. As keep on changing and changing, and at last you have a completely a smooth pipe for that value is coming 1 into 10 to the power actually 10 to the power minus 7 actually. Okay. And this is for the laminar flow, a straight line here, that because here this is just 64 upon RE. So if we keep on changing of the value, that this is how the value would change. And if you see this graph, that highest value of friction factor is 0.1. And after that, the lowest value is coming to here is nearly 0.03 something. Or you can say here at this, the bottom end 0.008 in terms of RE. So as you will increasing the value of RE, your friction factor or the losses due to friction are getting minimized. So highest loss are there in a low, mean the Reynolds number flow, in case of the laminar flow and all this. So here the friction factor value is high in this particular zone. After that, if you are the RE value has changed a lot, you say after some time, these are the straight lines. These are not changing further. So after 10 to the power 6 of RE, your values of the friction factors are not getting changed. If you read the corresponding value to this, you are here, fixed value here. So after 10 to the power 7 or 10 to the power 5, depending what type of the material is, and then it becomes independent of Reynolds number actually. Okay. So once you know
Yes,
your
sir.
friction factors, once you know the friction factors, now you have to design your pipeline, because your head loss would be calculated F L upon D V square upon 2G. So those are the losses due to friction. Now, what type of the problems could be possible in case of designing of the pipeline? One way that everything is given to you, length is given, diameter is given, flow rate is given, material of construction is given, everything is given. You are supposed to calculate your pressure drop. So if everything is given, so you can calculate first say friction factor, your pipe material is given, velocity is provided, flow rate. So you can calculate how much is head loss. Based on that, you can define what should be my pump, because that much head loss, because if that much is the head loss in 1 kilometer pipeline, you want to make the pipeline let's say 10 kilometer or the 100 kilometer. So in that case, that loss need to be compensated. So to compensate the loss, you are putting a pump. Let's say you might have seen some pipeline or gas pipeline or the something. Every 2 kilometers or 5 kilometers, you are putting a booster pump, a pump house. Why does it? Why do we need it? Because in that particular length, your pressure drop would be there only because of all these frictional losses, change in direction, bands, and those losses need to be compensated with the help of the pump. Otherwise, your fluid may not be able to flow at the another point, or sometimes the pressure will become too much low or equal to the vapor pressure of the fluid, that your fluid will convert it to the vapor and it will convert it to the gas. And in that case, you have designed a pipeline for the liquid. Now it is converted to the vapor. So your pump and everything would get failed. So you have to make sure a pressure inside the pipeline. First thing, it should have always a more than vapor pressure of the fluid at the given temperature condition, so that in order to avoid the vaporization, because it's not converted to the gas. Okay. Hello.
Yes, sir.
So this is the prime consider. You should make sure a particular vapor pressure, in the pipeline to avoid the vaporization. Vaporization create the cavitation in the pipeline, And sometimes you might have seen that your pump is continuously running and water is not coming out from the pump. That only because of that, some vapors are present in your pump impeller or casing, and your pump is not just designed for vapors, it is designed for liquid. So sometimes pumps burn out. So as you might have seen, the older time, the pump is need to put nearly 30 feet down of the ground, so that it have two reasons. One way is that to minimize the suction height, so that we will talk the later on. So first we are talking the designing of just to calculate the pressure drop. Pump we will talk the later on. So this is one problem. Another problem is that a person has given to you, this is how is this much is my permissible pressure drop. This much pressure drop I can permit. I know the length of diameter. I know the length and the diameter. Please tell me what should be the flow rate. This is the another type of the class 2 type of the problem. You are fixing a pressure drop. You know the how much is your pump capacity. You know the length of the pipe. You can control, because you can say after each 1 kilometer I can compensate the losses by the help of some pump. So that's much pressure drop I can compensate. So I know the pressure drop. I know the length. I know the diameter. Now you tell me what should be the flow rate. So you can calculate the flow rate. This V dot is practically Q. The another case is that you know the length, you know the permissible pressure drop, you know the flow rate. Now you have to design the sizing of the pipeline. So sizing of the pipeline, once you don't know the diameter of the pipeline, so each time you will take a diameter of the tube, do the calculation and check whether you are getting a desired pressure drop or not. If not, you have to again change the pipeline. So you keep on doing a iterative calculations to get the diameter of the pipeline. This is three type of the problem. Primarily is given in a basic fluid mechanics, but in the real estate it's not like that. A person, when you will be in a chemical plant or want to make a pipeline, he will say, I want to transmit this much of flow rate only. This much flow rate per unit time I want to transmit. Now it is your part what to do. It is your part means the person is interested only this much flow rate and this much should be the pressure available at exit point. Somehow the people are not interested in the pressure. If they are interested because they want to transport a material. So they are interested on the flow rate or mass. Rest of the part is your. Being a chemical engineer, being a pipeline engineer or piping engineer, it is your part to tell him this is the material of construction, because material of construction will change your roughness. This is the diameter, this is the length, because you cannot have each diameter pipe available in the market. You cannot have 1.1 diameter, 1.2. No, there are some standard pipeline sizes, diameter sizes, which are available commercially in market. If you are ending up some diameter, a fancy diameter by calculation, if you will go to the market, they will say you will not find it. So your all calculation is waste. So you have to always choose a diameter from available table. There are the tables which are commercially available worldwide. Okay. So you have to choose those diameters from there. Then you do the calculations, do the pressure drop. If it is well within the range, then your designing of pipeline is complete. Okay.
Yes, sir.
So we will do all this part, don't worry. So now before doing those calculations, these are some elements which always will be need in your the designing of pipeline, because pipe one you have a straight pipe. उसको connect करने के लिए what will you do? Because you cannot get a pipe of 10 kilometer length. Can you? So you cannot get. So you have a length also. Length is also fixed. The commercially available length of pipe is also fixed, because you want to transport the pipe from a pipe blowing part, जहाँ पे pipe बनता है, that need to transport to some particular place. So if you will go to the market, if you want to buy a pipe, you cannot buy a pipe more than 20 feet, I think, in your any of the shop available to you. Yes or no? Hello? So in market, you cannot buy a pipe of any length. 20 feet ka, the ready-made pipeline, the length. Rest of the pipe, if you want to make a longer pipeline, you have to make a joint. So joint can be done either with the help of some welding, or by need of some threading. Threading you need with the coupling. So I want to show all of them here. So what you have, this is part here, this is some change of size. This side you have a bigger diameter pipe at the inlet, and outer diameter pipe at this particular end. They are connected here. Now this connection could be of any type. It could be a socket, it could be a belt, it could be a flange. Have you heard these terms anywhere?
No, sir.
No, sir. Okay.
No, sir.
So I would show you all actually. So what you have, I just want to show here here you have a flow pattern. Now this is a actually जो reservoir, a tank. उस टैंक में आपने एक ये शार्प एंड लगा दिया. You have taken the outlet. So what you see here, the flow, the streamline is getting changed in that direction. The fluid is coming here, now it's getting bent. Again, this way, there's a sharp edge here. So wherever you will take a sharp turn, what you will do in case of your car, if you are running a car in a particular direction, you want to take a very sharp turn, 90-degree turn. What will you do? You are driving a car or vehicle, you want to take a sudden 90-degree change. What will you do in that case? What will happen to the energy of the car? Hello? Give some, the response fast.
So we may need some extra energy for
No,
that sudden
not
turn.
energy. Whatever energy is there of the car, you cannot turn at the same speed. If you will want to turn, your car will means collapse or turn down, right? Topple down, right? गिर जाएगा वो car, पलट जाएगा.
Yes.
So you cannot do it. So what you have to do? You have to put a brake. You have to slow it down. Too much slow, and then you can take a turn, right? So the energy, whatever the energy was available, that is getting destroyed or wasted actually. So wherever you have a sharp change, same thing would happen in case of fluid also. Here you have a sharp change. So this much energy, lot of energy will go as a base. So that is also a loss. Why is it a loss? Due to this change in shape. This is a sharp change here. Now, so the losses here in the energy would be high as compared to the losses here, because here you have given a slightly a curve. So whenever you want to turn a car, if you will take the radius, you need not to put a brake and all this, right? You are not doing anything. You are easily turning in a long radius, right? So means the energy is conserved. It's not getting waste. Now here you put a curve, so here the losses are slightly low. So I mean to say that whenever you will change the direction of the flow, or you will put the sudden contraction, sudden change, you will always have a loss. That's what I want to say here. Sharp change would be a too much high losses, and the rounded change or a curve change or a slow change would have low mean the losses. Is that fine here? Hello?
Yes, sir.
So in this case, you see the loss coefficient here 0.5. Here the loss coefficient is 0.03. You see how much time it went down. Almost you can say 10 times went down, right? By changing just the shape. You have just changed it smoothly. So I would say this is also one of the says here. You have a change here. Again, you have a sharp change. Again, you have a sharp change here. So this is the first one is called a contraction. Another one is called expansion. This means when you have a bigger diameter pipe, you are connected to a smaller diameter pipe. So this is called a contraction. Then you have an expansion, the smaller diameter pipe, and then you are connecting a bigger diameter pipe. So these two shapes are called, one is contraction, other one is expansion. Each would give the losses. Losses would be calculated from here. This is your loss coefficient or the head losses here. Kc b square upon 2. This Kc loss coefficient, this is calculated from these particular graphs. And this is the ratio here that is being calculated, A2 upon A1. Okay. Hello.
Yes, sir.
So these are the two things. Once you have one thing, you have learned here a contraction. Contraction is being used just to decrease the diameter or area. Expansion is just to expand it only. So you can say conversion and the diversion in that particular way. And these are the table, the corresponding graphs. So these would be provided to you. Don't worry for that. Now this is the another shape here. That is also a diversion, but this is a smooth one, a slightly tapered one. So you are changing a direction slowly, not a very abrupt change. With the help of the theta, if you will change the theta too much high, the losses would become too much high. So if you change the theta value, let's say 5 degree, 10 degree, 15 degree, so as theta degree will become more and more, your losses would also become more here. So that's what is being given the graph here, just to calculate the loss coefficient. This is, you see the band. Have you seen the pipe band? Just give me 2 minutes, okay? So you have the another class, but I want to complete something here. So this is the band here. You are changing a direction of the fluid very smoothly here. So if your diameter is larger than this R is more and more, your losses would become less and less. Best example was your car only. If you will take along the radius, you need not to put a brake and anything. So you can move at the same velocity. Same thing in case of this. If this R is large and large, your energy loss would be minimized, because you are not changing the flow pattern. Same streamline would continue. Okay. Compared to here you have a 45 degree sharp change here. So in case of sharp change, the losses would be too much high here. Now this is the table we have already talked about. So I compile it from various books, actually, from McDonald, Fox, Munson, White, and Sengel. So this is a consolidated table for the roughness for various type of the construction of materials and corresponding values of the roughness. So you can say glass here, smooth pipe, and you have all other material, steel, wrought iron, and then you have rubber tube, wooden here, drawn material, and casted material. Each will give the roughness. So we would end at this particular place here. Tomorrow we will talk what this is actually, means various type of fittings, something. Okay.
Yes, sir.
Fine. So various type of fittings, I will say. I will share you this PowerPoint also today, so you at least just scroll down it and keep your doubts ready for that, so that I can move it faster, because this is not a, because if you have associated somehow somewhere in your daily life, you would know everything. If you have just like a घर में you have a tap, you have a control के लिए knob होता है, that's called a valve there. So we will talk that in the tomorrow. Okay. Fine.
Fine, sir.
Okay. So
Sir, all these tables are important.
Yes, without that, how can you design the pipeline? You cannot. So you
So
need not to
many
buy here.
tables, so-
You need not to buy here. These would be provided. इसमें buy head का अलग कुछ नहीं है. In designing of pipeline, designing of anything, you need not to by-heart anything. Only thing you should know how to proceed the calculations. You should know the sequence and procedure, use the values, substitute them, do the calculations. Some basic value, at least you can know some basic value, just like a copper roughness, some idea, need not to by heart that also. इसमें by heart करने वाला कुछ नहीं, nothing, no need to by heart, everything would be provided. Okay, so we will end here.
Excuse me, sir.
Yeah.
सर सिलेबस पूरा कंप्लीट है या फिर कुछ पार्ट आप मतलब नेक्स्ट टाइम के लिए बोले?